Yesterday night, I was reading the Zephyr documentation on workqueue, and I asked myself, well, everything is clear. I'm wondering, should I make this talk? I mean, everything is in the documentation. But as I started Zephyr some 18 months ago, that was not that clear. Of course, we could say the documentation is improving dramatically, which it is. But it's also the case that when you are coming from some other operating system, you may have already some concept in mind. Or maybe this is a completely new concept for you, and you have to create your own mental picture first. So the purpose of this talk is to give you another way to look at workqueues and to demonstrate workqueues, also to look at some internal, so that when you look at the documentation, it is an help for the documentation and vice versa. I'm Loic Domaigne. I'm very glad to be here in Amsterdam in this Zephyr Developer Summit track. I'm a contributor to Zephyr in two ways. The first way, professionally, I'm working at Doulos, which is a training company. We are offering professional training services for Zephyr, but also in my free time, I hang on Discord and answer questions from users. Our goal is to help people to use Zephyr. Zephyr is not necessarily trivial, and we see the potential of this operating system, and we are trying to help people answering their question in order that they can use Zephyr. All right, so what is the agenda for today? First of all, we have a short motivation, why workqueue. Then we will look at a particular workqueue called the system workqueue. We will see some aspect of the system workqueue that we can also apply to other workqueues. We will work out together the design and consequences. We will look at Zephyr internal, so we'll step into the code. And we will see a few challenge and best practice. And we will finish this talk with the finish section, of course. I don't know if the timing will work, so maybe I will skip some of the slides. That's fine, you have the slide. I will also put a GitHub repo so that you can redo the example on your own. And we have Discord to continue the talk if there is a need to. All right, so first of all, let's start with a small demo about deadlines. We will just implement a simple timer, and then in order to add some drama, we will go to sleep. So here is the corresponding code. As you see, very simple. We define the timer here. We have our expiry function that will be called when the timer expires. And then in the main function, we start the timer. Here, after 1 second, we fire for the first time, and then we repeatedly fire every 250 seconds. And then we do that a certain amount of time, and then at the end, we stop the timer. And for the callback, the expiry function, here, as you see, quite simple. We have a counter, and we just do some logging. Really nothing super fancy here. So as you can guess, this works as expected. Okay, we get our logging every 250 milliseconds. Every 2 seconds, we get this deadline passing by. Okay, everything is fine. So now let's time to do the version 0.2 of our presentation. And here you see what has changed between the 0.1 and 0.2. Well, we just changed the demo version, and then we just had, for drama and suspense, to sleep before the logging statement. A sleep of 500 milliseconds before and after. And now if I rebuild the code and rerun, what happened, as some of you know already, we get stuck. So if you have already done embedded development before, you may have already a clue what's going on here. By the way, we could ask Zephyr to help us with this problem, in the project.conf, what we should do during development, there is one big config you should have, config_assert equal yes, that helps you to figure out if you are making mistakes using some API you should not use in certain contexts. You will get an exception, very useful. Also, two other things you could have enabled is to know from which thread the callback is being called using these two config options here. Very useful because you will see if it's called from a thread or from something else. So if I rebuild the applications and run it, then here we will see what's going on. So now we see that our callback function, as a matter of fact, is not called inside the thread. It's called as part of an interrupt service routine. And as you know, we cannot do whatever we want in interrupt service context, and this is exactly what we see with these exceptions. All right, so yes, always think about who is calling your callback. Zephyr make it very easy with the subsystem to just register a callback that get called, but the subsystem has implemented for you the whole interrupt service routine machinery and so on and so forth. So here we have seen the practical tips already. And the problem in interrupt service context, we cannot do whatever we want. We should not block, for example. So now, how do you know which API you can use in interrupt service context? This is part of the documentation. There is a flag here, you will see. If your API can be used in interrupt service context, you have this ISR OK. And when we run in interrupt service routine context, here this is what will this preempt any user thread, any cooperative thread. This is what runs on the system. The only possibility is to be interrupted by another interrupt. So it's not a good idea to spend 3 hours to solve the Schrödinger equation, for example, because you will block everything else. So we should keep interrupt service routine short and fast. And also, we have limited set of functions as we have seen. So the question, what if a complex processing is needed? And this is where we come to system workqueue. So that's something also very typical if you are coming from embedded OS, you know that. When we have an interrupt service routine, typically there are two parts. The top half, this is where you need to be this is time critical. Typically, you have the interrupt disabled, and here this is where you do the hardware-specific tasks, like clearing some masks, for example, for the DMA. And then they come the more, I would say, less time-sensitive work, but that may be more time-consuming. So if you take, for example, a network driver, that's typical. First, the network-wide driver will clear the DMA flag, etc. And then there is some bookkeeping of the DMA buffer, and then this gets passed to the TCP/IP stack. And so the idea is this bottom half here that is less time sensitive. How about delegating that to a separate thread? And that's also a classical pattern in embedded OS. We have here the interrupt service routine where you do your top half, and then there is some signaling that could be a semaphore, and the bottom half is implemented as a separate thread. Another possibility is to have some kind of queue, and then you send some item to the queue, and this item could be like a kind of request you want to process. So there are many ways to achieve this splitting. And of course, Zephyr has the possibility to do this splitting, which is workqueues. So what are workqueues? This is a thread plus some queue to store the workqueue item, plus some synchronization mechanism. What is a work item? That's simply the function you want to offload. So and work item is submitted to the queue. So what happened? Your workqueue thread will take the work item and we'll call the corresponding handler you have associated. So you see how it works. Here we define a work item with a macro keyword defined. Here we attach the bottom half. That's the code normally that we want to offload here. that we have put in a separate function, and then in the interrupt service routine, you just do the k-work submit. So you submit this work item to the queue. So here, a work item in Zephyr, it's basically the function you want to offload. Okay, so demo number 3. So what has changed between demo number 2 and demo number 2? Sorry. The only difference is we have updated the version number, of course, and now we have removed the code. That's the code we want to offload. We have simply the k-work submit. Here, the code we had before in the interrupt service routine, we have put it in a separate function, and we have attached a work item, the corresponding offload function here to a work item that we are submitting in the ISR. So quite simple to use, and here we are using a special work queue called the system work queue. That's a work queue that is predefined by Zephyr. And yes, so maybe what I will do, I will also change the project.conf to have the shell. So now if we run, hopefully we won't have this blockage anymore. Okay, no, that's fine. Now we are getting at counter 10 instead of counter 8. That's because of the sleep 500 milliseconds we are doing before. Right. What do I want to show you? Maybe the Zephyr shell for those who do not it. Just need to check the dev PTOI2. Okay, let's do that. Okay, I'm just rerunning. So here I have enabled the shell. Sorry. I have enabled the shell, and I don't see the output because now that's 3, of course. Oh. So now this is not working. Okay, that's the live demo stuff, as usual. We fix it quickly. Sorry for that. Okay. Right. So now I can see we have this sysworkq thread that gets started, and we see that's priority -1. Okay, what are the design consequences of using this sysworkq? So first of all, a short recap. In Zephyr, we have 2 kinds of thread, preemptible thread and cooperative thread. The preemptible thread has a positive or 0 value for the priority, whereas cooperative thread have a negative value. And the lower the value, the higher the priority. And the difference between preemptible thread and cooperative thread is what happens if you have a thread here running and there is an interrupt service routine that makes an higher priority thread ready. In the case of preemptible thread, when you return from the interrupt service routine, you will schedule this high priority thread. Whereas in the case of cooperative, you will return back to the preempted thread, and the thread will run until it either blocks or it explicitly uses k-yield. Cooperative thread, the advantage is we know when the preemption will occur. But this introduces a delay for high priority thread. Whereas for preemptible thread, we don't know, it could happen potentially at any time, the preemption, but we don't have this delay. So the system workqueue we have seen is using cooperative thread. Also, the system workqueue, as the name may imply, is shared by the entire system. You don't have to believe me. You can just run this grep command on the Zephyr main repo, and then you will see that. So here, the design consequences of what we have just discovered we have many subsystems that are using the system work queue and also drivers, and they all can potentially enqueue some work item to the queue if we are using the system work queue. So first of all, on the positive side is the nice things about the system work queue. We have only one thread, and we can potentially serve all these subsystems and drivers, so we are saving resources. It's easy to use, as you have seen, and the fact that it's cooperative scheduling, it's behave ISR-like. But now on the other side of the consequences, we should keep the processing short. If we block here, we will block all potential other work item that has been queued. That means we are introducing some further delay. And of course, ideally for the system work queue, when it has processed one item, it should call kyield if another cooperative thread has been making runnable that has a higher priority. So now you will say, but you told us it's good to offload if you have a long processing time, and now users say keep processing short. Okay, in this case, you should create your own dedicated work queue. We can do that. We can set the priority. We can have preemptible work queue. It's not a problem. There is something called meta-IRQ. I don't want to spend too much time on it. The idea is to have a thread that can preempt cooperative thread. They are very specific. They are really meant for driver. Please don't abuse them in application as high priority preemptible thread. That's not meant to be like that. We can discuss that in the QA session if you want. So I skip the slide here. Okay, so now let's have a look at some Zephyr internal. Let's see how that works, this system work queue, and learn a few things along the way. All right. So I have prepared that. So the best way to see what's going on, I will jump into the code here of Kwork Summit. Oops. So we see, that's Kwork Summit to queue here. So, yeah. So here, that will be the function we would be using if we would create our own work queue. So I think it's interesting to first look how this submission takes place. So here we go to the internal function. There are some bookkeeping that's not very important. We see there is a log that is taken for each work item. And then there is the submit to queue locked. And here that is being interesting already because we see, there are some flags. We can do something like cancellation. And this is also checking if the work item is already queued. If it's not queued, what will happen? It will then insert it. And here, if we look at this function, we will see that the work item gets inserted into a list. But if it's already queued, we see do nothing. So what is the consequence of that? If you do 2 Kwork submit in a row, only the first one will be taken into account. You won't run your offload function 2 times. That's per design, and that's because we are using a list, and if we would add that into 2 times, we would have an inconsistency in the list. We are not copying the corresponding item. That was interesting already to see. There is also something else I want to show you is the system work queue. So if I click on the symbol here, cases work queue, this is how we can see how it gets started. We have this initialization. So here it initializes the system work queue. We see there is this no yield. So that's a configuration item we could have for the system work queue. And per default, this is enabled. That makes sense if you have a cooperative thread. And then what we see is that this cases work queue init is called using sysinit. And sysinit is a macro you can use to start a function at boot time. So here what happened is the system work queue is automatically started by Zephyr. But that's half of the story. Because the Zephyr kernel is built as a library, so the driver, by the way. And the linker, in the final linking stage, will look and will see if you are using this symbol here, yes or no. If you say, oh, nobody is using the sysworkq, it will throw away all the symbols inside this system-workqueue file. And so, if you are not using the system-workqueue, you won't get the penalty in your final image. All right. So, this is a summary what we have just seen. We have config item. We have the we have also workqueue. We can use this API if we want to create our own workqueue. We have seen a workqueue item. We can submit only once, and also we have seen the magic behind the workqueue. And thank you, Andy, for the explanation on Discord. Right. Okay, let's have a look at a few challenges. Unfortunately, I've stopped my timer by mistake, so I don't know what I'm doing for the time. How many time do I have left? 15 minutes. Okay, that's fine. So 5 minutes. Okay, let's do that. All right. So some challenges. So first of all, some surprise. As we have seen, if we submit the item 2 times, only the first time work. Well, that's described in the API documentation. And here, a small surprise, most of the Zephyr kernel API normally return 0 if OK, and a negative value if there is an error. That's the case for the workqueue, but also we have 1 and 2. These are not error code. That's something that is expected to happen when you use workqueue per design. Also, another challenge is how do you pass data to the work handler? How do you do that? A typical mechanism, so we could have dedicated data passing mechanism, but a way you will find in Zephyr is to create a structure where you have your work item, which is part of the structure, plus the other fields. And what you can do then, you would use the kWorkInit to initialize the work item, and then in your handler, you get a pointer to this work item. So you can use the container of macro to say, okay, look, item is a pointer to the field work of the struct device info, and what container of will give you is a pointer to the structure, and then from there you can recover the other field. But be careful here. Immediately, if your data is mutable, you will have a race condition that you need to handle. So maybe if you are lucky, you can use an atomic type. If not, then you will have perhaps to use spin lock and this kind of synchronizations. Challenge number 3 is, and this is a bad design, what I've done with the 500 millisecond sleeping in the workqueue, because I'm blocking other item in the queue. So in this case, there is a solution called Delayable work. And what you can do, you can schedule a work item to be added later in the queue. And there are typical usage. So here, for example, for debouncing or event aggregation, for periodic or scheduled activity, data collections, and timeout management. Here I gave you some examples from the Zephyr code 3.2 that you can look at. They are relatively simple to understand. And finally, I want to finish with canceling. Here, sometimes you want to cancel a work item. Typically, you unplug a USB or you have a wireless communication that suddenly disconnects. You need to cancel the request. So we have kwork cancel, and the same for the delayable work. In this case, the challenge that can happen is that the work item is being processed while the cancellation occurs. So that may or may not be a challenge. Sometimes you can detect that in the work handler. Sometimes you have to do something. And the technique is to use, to embed a cancellation flag that you can then check here in your work handlers. So I won't go here too much into detail. We can do that in the QA session if you want to. And there will be a GitHub repo. It's there, but it's not yet, it's still private, that you can access and redo this example on your own with the slide, and then if you have further questions on Discord. All right, to finish this talk, we have seen workqueue. We can defer long non-critical work from interrupt handler. Typically, it's found in driver code. The submitted work is serialized and executed in a FIFO manner. We have seen the system workqueue is simple to abuse. Cooperative thread plus share, so be careful. We can handle safe cancelling, dereferring and rescheduling, but we introduce latency, and ending of concurrent work is quite complex. So there are alternatives, and two of them I want to mention. For application, you could use workqueue for application, but then I would suggest look at ZBus. ZBus is optimized for embedded application if you want to communicate between threads. It's real-time aware, it's scalable, and it promotes component decoupling. And we have the chance, Rodrigo, which is the author of ZBus, is there this week. There are 2 slots on ZBus. So look at ZBus if you don't know what it is. And if you want to do high-performance I/O, you want to stream, you have multiple sensors, you want to get the streaming and do fusion, etc. Well, workqueue won't bring you very far. It's super difficult to get that very efficiently. And there is another framework called RTIO that you can use for optimized I/O transaction, real-time aware, low latency, and for concurrent or batch-like I/O flow. And I wanted to talk about P4WQ. I won't, because I discovered, okay, that was part of RTIO, but the RTIO developer have removed that, I think, beginning of July. And we have the author of P4WQ in the back, so just ask Andy in this case. All right, thank you very much for your attention. We are at booth 26, sorry, if you need professional training. Booth 23 to discuss Zephyr, demo, and more. Today at 5:20, we have the Meet the Maintainer. Join Discord, and now it's time for questions. Thank you very much. Any question? Yes. I think I have seen some pattern like that where you. I'm not sure. I don't know.
I'm going to guess no. I don't. For sure, there's no specific protection. So yeah, I would not. Vote us on Discord is a great place to ask questions like that. But I'm 90% sure that the answer is no. But it's probably fixable.
What I've seen is the application do the reservation, and then the workqueue. The application knows about the buffer and knows when to freeze. But the TCP/IP stack is interesting for that. So this is where I had my vote. Thank you, Andy. Okay, more questions for Andy, please. Yes.
I have a question on the system workqueue itself.
Yeah.
How do you deal with the fact that a lot of device drivers are actually using the system workqueue, and so that the system workqueue as a whole becomes the bottleneck of the system?
Yeah.
Are there any things that you can do to either monitor the load on the system workqueue, on how to, or also to how to mitigate such a load issue?
Okay, I just repeat the question. The question is about the system workqueue is used by a lot of drivers, and so what can happen is you are getting latency, and how you monitor the usage of the system workqueue, and what can you do to mitigate the problem? That was your question, I think. We are not monitoring the system workqueue. There has been a proposal on one issue to have something like monitoring the system workqueue. Here, the point, and you are right, it's also one issue in the Zephyr that everybody is using the workqueue and we have this latency. So my understanding is that we are working to decouple that. RTIO is in one part of the solution. Another thing is what I would really recommend is if you have a latency problem for your specific application, if you can afford it, dedicate your own workqueues. So that would be my answer. More questions?
You can just use tracing to see when the work is occupying the CPU and when it's not. That way you can estimate.
There are possibility to discover that the workqueue is hogging the CPU. But I think the question was here to have a kind of automatic, a kind of watchdog kind of mechanism available. But yes, absolutely, a good remark. Thank you. More questions? Yes, thank you.
What's the general direction that the workqueues are going to go in the next Zephyr iterations? You've shown the lock function, and you've shown that for quicker applications there is RTO available.
Yeah.
So what would be the specific use case for workqueue compared to
Very good question. So the workqueue still is used, I guess, for certain drivers. I see, for example, the network drivers are using the workqueue together with the DMA. This is a bit of work to get that properly done, and there are often bug reported against drivers. For me, that's one of the legit, as we say these days, case for workqueues. But then, yes, again, there are limitations. If you need to have something very efficient, like you do streaming, for example, then the RTIO is better. And I don't know if there are some developer here in the row on RTIOs working in this topic. No, unfortunately not. Okay. I mean, it will be interesting to see how it will change in the future, this architecture. Yes?
I've worked with different ARCO systems that have two workqueues, typically a low priority and a high priority one. Why doesn't Zephyr use the last time?
That's a good question. I'm too young to know that.
What Zephyr does is because you create your own workqueue.
Yes.
There's one system workqueue. It tends to be, most subsystems use it as mostly just like a junkware, any kind of work that you've got. Unfortunately, it's configured, as it's mentioned, as kind of more like a bottleneck. It's actually very time-sensitive. So it might be a good idea for us to have it, but right now it's a toolkit for us.
Typically with the networking, you want to have it separated because you don't want to have a GPL that then screw up your throughput.
Right, yeah. Well, the network stack has its own things, so it doesn't use.
Yeah. So I just repeat for the people watching. So the question was about some authors have two workqueues, high and low, and why does Zephyr has only one workqueue? I say, okay, I don't know. And the answer, yes. So we can always create our own workqueue. That's true. And then I forget one part of Andy's answer. Sorry for that. What was the other part?
Networking does its own stuff anyway.
Bluetooth has that one that
Yes. All right. Oh, one more question. No, thank you.
This regards to Demo. In the first example, you saw in the logging that it was an interrupt.
Yeah.
Printed the information, then you changed it as the workqueue.
Yeah.
Somehow in the logging, there was still displaying that it's an interrupt.
Oh, really? Okay, I missed that.
Because I was expecting.
No. Okay. That's very good. Very good question. So here what you see is you have this whoosh. The whoosh logging is coming from, no, maybe I should look at main. The whoosh logging is coming from the function, the callback, timer callback. So that's an interrupt, but the deadline passing by should be in the system workqueue thread, and this is what we see here. Thank you. All right. I think it's time for lunch. You know that time is an illusion, and lunchtime even more so. Thank you very much. Enjoy the week. Thank you.